Let us discuss the definition of absolute extrema for functions of two variables. So suppose we are given the function f of x, y, its domain D inside the plane R2, and the point x0, y0 inside the domain D. We say that f of x0, y0 is the absolute maximum of f if f of x0, y0 is greater than or equal to f of x, y for all points x, y inside the domain D. On the other hand, f of x0, y0 is called the absolute minimum of f if it is less than or equal to f of x, y for all points in D. And we say that f has an absolute extremum at x0, y0 if f of x0, y0 is either the absolute maximum or the absolute minimum of f. Let us compare this with the definition of relative extrema of f. In our definition, if we replace the word absolute by relative, then we also have to replace the word the by a relative maximum or a relative minimum. That is because there can be many relative maximum or relative minimum of f. Compare with absolute extrema, we say the absolute maximum or the absolute minimum because there can be only at most one absolute maximum or minimum of f. Another difference between absolute extrema and relative extrema is the condition that x, y should be inside the domain D. Recall that in our definition of relative extrema, instead of the whole region D, we only consider points in some disk containing the point x0, y0. That is why we often call relative extrema as local extrema and absolute extrema as the global extrema of f. Now, one way to assure that the absolute extrema of functions exist is by using extreme value theorem or what we call EVT. So first, let's recall the EVT for f of x. If the function f of x is continuous on the closed and bounded interval a, b, then we are sure that the absolute extrema of f on that interval exists. And the EVT for f of x, y is analogous. We have if f is continuous on a closed and bounded region instead of interval, region D, then we are sure that absolute extrema of f on the region D exists. Before we continue, what are closed and bounded regions? For illustration, this colored region is an example of a closed and bounded region. It is closed because the boundary is included, and it is bounded because we can enclose it inside some closed disk. Meanwhile, this region is not closed because not all of its boundary are included on the region. For our third example, the region extends upward, so we cannot enclose this inside the closed disk, and so it is not bounded. Now, if we are sure that our region D is a closed and bounded region, then we can use the following steps in finding the absolute extrema. First, we find all the critical points of f lying inside the region D. Next is we partition the boundary of D to a union of curves. For instance, if we have this square region D, then we can partition the boundary into the union of its four edges. We restrict f on each curve, thereby getting a function of a single variable, either in terms of x or in terms of y. Then we find all the critical points of the resulting function. For our third step, we have to list all the intersection points of the boundary curves of D. So in our example, the intersection points here are the vertices. Lastly, we evaluate f at all points obtained in the steps 1, 2, and 3. The largest among these values is the absolute maximum value of f on D, while the least is the absolute minimum value of f on the region D. For our example, let us find the absolute extrema of f is equal to x squared plus 3y squared minus 4x minus 6y on the triangular region with vertices at the origin 4, 0 and 4, 4. Note that a triangle is closed and bounded, and f is continuous everywhere since it is a polynomial function. Hence, f has both absolute maximum and absolute minimum values on our triangular region due to the extreme value theorem. So first, we look for all critical points of f inside the region. There are no points that makes f undefined, so we solve for the system of equations f sub x is 0 and f sub y is 0. Our f sub x is 2x minus 4, and f sub y is 6y minus 6. Solving these equations, we have x is equal to 2 and y is equal to 1. So 2, 1 is a critical point of f, and it is a point that lies inside the triangular region. For our second step, let us partition the boundary of the triangle as a union of its three edges b sub 1, b2, and b sub 3. The curve b sub 1 is a subset of the curve y is equal to 0. We restrict f on this curve, so we have f of x, 0, which is equal to x squared minus 4x. Then we get the critical point of x squared minus 4x, so we have to find its derivative. So f prime of x, 0, that is 2x minus 4. We equate this to 0, so we get x is equal to 2. We are on the curve b sub 1, y is equal to 0, so our point here is 2, 0. b sub 2 is a subset of the line x is equal to 4. So we have f of 4, y, that is 16 plus 3y squared minus 16 minus 6y, or simply 3y squared minus 6y. Then get its derivative, we have 6y minus 6, equate it to 0, so we get y is equal to 1. Again, we are on the curve x is equal to 4, so our point is 4, 1. For our last boundary curve, it is a subset of y is equal to x. So when we restrict f on this curve, we have f of x, x, that is x squared plus 3x squared minus 4x minus 6x, or if we simplify, we have 4x squared minus 10x. Let's get its derivative, so we have 8x minus 10, equate it to 0, we get x is equal to 5 over 4. Since we are on the curve y is equal to x, we have the point 5 over 4, 5 over 4. Therefore, the points on the boundary where extrema may occur are 2, 0, 4, 1, and 5 over 4, 5 over 4. For our third step, we list all the intersection points of the boundary. The intersection points here are the vertices of the triangle, so we have the origin 0, 0, 4, 0, and 4, 4. Finally, we compare all function values at the points obtained in steps 1, 2, and 3. I leave it to you to check that these are the function values. Thus, the absolute maximum of f on our region is the largest function value, so that is 24. And the absolute minimum of f on our region is -7. As an exercise, find the absolute maximum and minimum values of f on the set D. Before you proceed with the video, you can pause the video and answer these exercises. Let us consider this example. Let us find the absolute extremum values of 4x cubed plus y squared on the ellipse 2x squared plus y squared is equal to 1. This example is different from the previous one because here we want to find the absolute extrema over all points that satisfy the equation for the ellipse 2x squared plus y squared is equal to 1. So in this case, what we wish to do is to maximize or minimize the function f subject to the constraint, which is the ellipse. To solve this example, we use the method of Lagrange multiplier. Given a function f of two variables x and y, we solve for all the points x, y that satisfy the system of equations f sub x is equal to lambda g sub x, f sub y is equal to lambda g sub y, and the equation for the constraint. Lambda here is not a variable, it is some constant, which we refer as the Lagrange multiplier. After solving the system of equations, we now evaluate f at all points obtained in the step 1. The largest of these values is the absolute maximum value of f subject to the constraint, while the least value is the absolute minimum value of f subject to the constraint. The proof as for why this method works includes concepts which are not discussed, so let's just trust and use this method in our example. We already have the given f, and our constraint is 2x squared plus y squared is equal to 1. So here, g of x, y is 2x squared plus y squared, and k is equal to 1. For our first step in our solution, we solve for all the points that satisfy this system. So this system includes partial derivatives of f and g. Solving for the partial derivatives, first let's start with f. F sub x is equal to 12x squared, and f sub y is equal to 2y. Then copy the constant lambda. Now let's solve for g sub x and g sub y. G sub x is equal to 4x, and g sub y is equal to 2y. Then just copy the constraint as our third equation in the system. So to solve this system, let us start with the second equation since it looks simple. So here we have 2y minus lambda times 2y is equal to 0. Then we can factor out 2y. So we have the product of the factors 2y and 1 minus lambda. They are equal to 0, so we get y is equal to 0 or lambda is equal to 1. For our first case, we have if y is equal to 0, then we can substitute this in the third equation. So we have 2x squared plus 0 squared is equal to 1. So we obtain x is equal to plus minus 1 over square root of 2. Therefore, 1 over square root of 2 comma 0 and negative 1 over square root of 2 comma 0 are solutions in our system. So that is for the case where y is equal to 0. For the second case, where lambda is equal to 1, we can substitute this value of lambda on the first equation. So we get 12x squared minus 4x is equal to 0. Then factor out 4x, so we have 4x times the factor 3x minus 1. Equate each factor to 0, so we get x is 0 or x is 1/3. So here in our second case, we have further subcases. First is when x is 0, then we can substitute this value on the third equation in our system. 2x squared, so we get 0, plus y squared is equal to 1. Solving for y, we have y is equal to plus minus 1. Therefore, the points 0, 1 and 0, negative 1 are also solutions in our system of equation. For the second subcase, we have x is equal to 1 over 3. Using the same third equation, 2x squared, so since x is equal to 1 over 3, we have 2 over 9, plus y squared is equal to 1. Then solving for y, we get y is equal to plus minus square root of 7 over 3. Thus, we also consider the points 1/3, square root of 7 over 3, and 1/3, negative square root of 7 over 3. After solving that system, we now finally evaluate f at these points. This is just evaluating function values, so I leave it to you to check that these are the following function values. Note that the absolute value of the square root of 2 is greater than 1, and 25 over 27 is less than 1. Therefore, subject to the constraint, the absolute maximum value of f is square root of 2, and its absolute minimum value is negative square root of 2. For the following exercise, use the method of Lagrange multiplier to find the absolute maximum and absolute minimum of the given functions subject to the given constraint.